Hello everybody, and thank you for being here. I am Alexandros Tsouros. I'm currently during my first year as a PhD student here at the Institute of Astrophysics at Fourth and the Department of Physics at the University of Crete, and I'm working under the supervision of Professor Vasiliki Pavlidou. Sorry. Okay. So in this talk, I will mainly try to motivate the work that I have been undertaking lately in my attempt to study the galactic magnetic field and its 3D realization. So an initial starting point is to try and explain why we care about it in the first place. Well, the galactic magnetic field plays a crucial role in a variety of astrophysical phenomena, to name a few. And of course, the list that I'm going to show is not exhaustive, but it's representative of my main interests. So for instance, in high energy astrophysics, in particular in the study of cosmic rays, the knowledge of the 3D structure of the galactic magnetic field is necessary in order to be able to backtrack the trajectories of charged particles and figure out the location of their sources in the sky, something that is still an open question. And in cosmology, in the study in the knowledge of the structure, the 3D structure of the galactic magnetic field is crucial in order to decontaminate CMB polarization measurements that aim at detecting B modes predicted to be imparted by inflationary gravitational waves. So as you saw earlier in Gino's talk, the magnetic field aligns dust particles, and these polarize the microwave radiation, contaminating the measurements. So in order to construct a tomographic map of the magnetic field, one needs to deconvolve the polarimetric effects of different clouds in between stars with measured properties. So the model in its simplest form is the one shown in the figure here. The dust cloud is modeled as a screen perpendicular to the line of sight with a magnetic field of some plane of the sky orientation. In between the dust clouds, the neutral medium is so hot that the hydrogen is ionized. Moving towards the dust clouds, temperatures are such that we have recombination of hydrogen. And at where the screens are, the dust clouds are, there is a phase transition where the dust particles form. These are aligned by the galactic magnetic field and thus act as a polarizing screen. Typically, their thickness is much smaller than their distances, than the typical distance between them, and thus we are allowed to model them as screens. Now, combining polarization measurements from the upcoming Pacify survey, along with distance measurements from Gaia, gives us a way to infer the plane of sky magnetic field as a function of distance by subtracting the polarization effect of each dust cloud. So now, in what will follow, we'll try to describe attempts to implement a specific algorithm, namely the Bayesian Blocks algorithm, to the above problem, that is, given combined optopolarimetric data and distance measurements of individual stars along a given line of sight, can we reach a conclusion about the distribution of dust clouds along that line of sight? So let me try to very, very briefly explain what the Bayesian Blocks algorithm does. So the algorithm was developed initially to analyze the structure of time series data, and hence is inherently a one-dimensional algorithm, although generalizations for higher dimensions exist, at least in theory. The problem it attempts to solve is the following. So suppose you're given a data set that consists of event data in one dimension, events observed in some time interval. Further, this data set is corrupted. It has some noise due to some intrinsic processes, instrumental effects, and so on. The question is, what is the optimal segmentation of the data set? Now, I will have to define what the optimal segmentation is. It is typically a segmentation of our 1D data space, which maximizes some quantitative expression. In simpler words, and if it's qualitatively, it is the task to find the change points of the dataset statistical properties. So here's a very simple example that I created to illustrate the algorithm. So just to illustrate what an optimal segmentation is. This is one of the things that is very easy to understand once you see it, but it's quite difficult to define. So here, this is a step function. The function is 1, 2, 3, 4 for every 10 integers. It is obvious by eye inspection what the optimal segmentation is in this case. It's just the segmentation of the x-axis into tens. So the statistical properties of this cell is different from the statistical properties of this cell. So there is an optimal segmentation. So running the Bayesian Blocks algorithm, we're able to find what we call the optimal segmentation with the cells of that characterized by different statistical properties within each. Briefly, how it works is that we start with a given segmentation and apply criterion to each neighboring cell. If that criterion is met, we merge the cells, and if not, we leave them as is. We keep going until the criterion is met for every set of neighboring cells. So that's basically how it is. And the criterion is calculating the posterior probability that you can calculate analytically, either for time series data or step function data. So that's essentially how it works. And now let us be kind to ourselves and assume that we live in an ideal world where there is no observational noise, and whatever deviations we have from a perfect step function is only due to intrinsic physical processes. We will perform the Bayesian Blocks algorithm and see whether we get the correct segmentation, which is interpreted as a statement about the location of the dust clouds or screens along the line of sight. Okay, so this is what data would look like if we lived in the Platonic realm where there are no observational errors. Whatever deviations from a perfect step function exist are only due to intrinsic reasons. For instance, the fact that the magnetic field on each screen is not a constant, but there are deviations due to turbulence. Wherever you see an abrupt jump, can you see my cursor here? Whenever you see an abrupt jump, it signifies the existence of a screen in each Stokes parameter. Notice that in this case, the Q Stokes parameter is blind to the existence of a second screen because there is a jump here only in the U Stokes parameter in red, and there is no jump in the Q Stokes parameter. This is something that an effect that can be seen in actual data, or is expected to be seen in some cases because of the orientation of the cloud. So again, I'm showing this cartoon here just to make you understand how this data is gotten. Essentially, the data is gotten in the following way. Okay. So we look at 1 degree in the sky. We take all stars that have an R magnitude less than 16, which is a limiting magnitude of Pacify. From the Gaia emission, we have their distances. And what we do next is put in screens by hand with a given polarization fraction. We have 3 screens here, as you can see. And each has a 0.2% polarization fraction, and then calculate the effect on the polarization due to the screens of starlight. Of course, we assume that the starlight is inherently unpolarized when it leaves the parent star. Then we perform the Bayesian Blocks algorithm, and sure enough, we are able to find the location of the dust clouds. It is important to note here that the only input that we give is the data. We make no prior assumptions about the distribution of the clouds. Okay, so now what we do is we run the algorithm, we give the data we feed the data into the algorithm, and the screens are found. So it works quite well, and we're very happy that it works in this simple case. So with that, it seems that when we look at the mock data with intrinsic scattering only, the Bayesian Blocks algorithm seems to find the optimal segmentation. However, every statement that relates to data, like this segmentation is the optimal one for the given data set, should also come with some quantification of the certainty of that statement. The Bayesian Blocks algorithm has no intrinsic way of quantifying how certain the end result is. In order to produce that, we need to perform some bootstrap sampling. So what happens is that we take the data set and sample out n stars from a uniform distribution, and then we perform the algorithm. We save the location of the first edge that was found in an array, and the second edge that was found in a different array, and so on, for every edge that was found during the process. We do that many times, let's say 1,000 times or 10,000 times, and each time we concatenate the edges to each corresponding array, and then we plot the histograms for each array and see what we get. So this is the output of our program. for the U-Stokes parameter only. We can also perform it for the Q-Stokes, but in the interest of time, I will only focus on the U data here since it can see all three screens. With blue, we can see the first edge that was found throughout the bootstrapping process. So there are like 1,000 first edges because we did the bootstrapping procedure for 1,000 times. With red, we see the second edges here, and with green, we see the third edge. The black vertical lines signify the actual positions of the screens, and we see that the algorithm is able to find the location of the screens every time for every screen. So in this case, it works quite well. However, keep in mind that we have only been using intrinsic scattering and we haven't been taking into account observational errors. And however, usually nature is less kind to us, and more realistic data sets also have a significant amount of observational noise. So this is the same data, but they are now corrupted by observational noise, making it closer to what we would expect to observe. As you can see, the data is a lot messier and the segmentation becomes much less obvious than it was before. The data is gotten as follows. We assume a given exposure time and calculate the uncertainty according to this fit, which was taken from robable data. Then we choose a point from a Gaussian with that given uncertainty and create the more realistic data set. So as expected, the more realistic scenario is a lot messier, and at least by eye, it is impossible to find any significant structure in the data. It does, however, pay to see what the result of the Bayesian Blocks algorithm would be. And this is the result of our program. This is the output of our program for the U-Stokes parameter again. With blue, we see the first edge that was found throughout the bootstrapping process. Again, the same thing, the first edge 1,000 times, second edge with red another 1,000 times, and so on. The black vertical lines again are the actual locations of the screens that we put in by hand. We see that the algorithm is able to find the location of the first two screens quite well. The first edge converges to the location of the first screen, so this is found easily in the noisy data, which is quite good. The second edge, again, is sort of converges along with the third edge, converges to the second screen. And then as we move to the other edges, we lose touch with reality, and the third screen is missed completely. In contrast to the case where only intrinsic scattering was included, while we do get hints of the existence of two clouds and an approximate knowledge of their locations, the third cloud is missed entirely. The reason for this is that as we move further away and towards the third cloud, the uncertainties become comparable to the polarization fraction of the cloud, as you can see here. And so we're unable to detect it. In this figure, we see a color map of the number of stars in a given distance with a given uncertainty sigma u, as well as the median sigma u as a function of distance, which are the red dots here. Further, with the white crosses signify the polarization fraction of the screens as well as their locations. And as you can see, at about 700 parsecs, the median here, here, the median uncertainty in U starts becoming comparable to the polarization function of the screen that exists there, and that possibly explains the inability of the algorithm to find the third screen. So in the interest of time, I will. So we have seen how the Bayesian Blocks algorithm might be generalized from its usual application to time series data in order to perform a 3D tomographic study of the magnetic field of the galaxy, as well as perform dust cloud cartography. When the polarization data deviates from a pure step function, only due to physical phenomena, deviations of the magnetic field, as I mentioned, due to, for instance, deviations of the constancy of the magnetic field due to turbulence, the algorithm is able to recognize the existence of the clouds very easily, and as well as their locations. However, when observational errors are included, the performance is obviously not as good, but it still provides insights with respect to the existence of clouds, especially ones with high enough polarization fraction. This is interesting because we make no prior assumptions in this enterprise here. We don't assume anything about the existence of clouds. The only input is the data. So that's promising. And the future work is to make this study a little more concrete, use various data sets, and see in what region of the observational parameter space the Bayesian Blocks algorithm provides a good tool in looking for dust clouds along a given line of sight. Therefore, making it a little more strict, and also see when it can be used as a tool. That's all from me. Thank you very much.